So we're now going to come up with the second kinematic, what I call the second kinematic equation, and the equation is going to relate the two variables of position and time. Let's take a second and make it clear what we mean by variables and initial conditions here. So the things that are initial conditions that will not change for a particular problem are where you start. So your original position. How fast you were going at the start. Your original velocity. And for us, in these problems, our acceleration is an initial condition. What about the things that will change as time goes on? And that's the hint. There's the first one. Our variables are, the most fundamental is time. Can't really keep that from changing. And as time goes on, our position could change. So we'll call this our, quote, final position. But that's kind of up in the air depending on how long we've been going. And the third one, and I hope you can see this on here, is your final velocity. Which once again, I really don't put final there because if the time changes, this is going to change. So these three change, time being kind of the thing that drives it all, but these will change. These will stay the same for a given problem. The first kinematic equation that we looked at related time and velocity. The one we're going to create now is going to relate time and position, and we don't want to deal with velocity in this equation. So here's where we start. We'll start with, where we left off in the last video, which was that the final velocity is equal to the acceleration times the time plus the initial velocity. But I also know, and this comes from the beginning of last video where I said remember something, and it's back. By relating two equivalent expressions for average velocity, I come up with the following. I know that v plus VO divided by 2, that's one way to look at average velocity, is equal to x minus XO, the displacement, divided by the time, which is also average velocity. So what we have here are two equations. We can use the fact that I have two equations to relate this situation to get rid of V final, that is. Not worried about V initial, that's fine. So what I'm going to do is this. I'm going to take this and I want to solve it for V. So we're going to start by multiplying both sides by 2. So I get V plus VO equals, let's go ahead and, let's distribute the 2. And let's do it, you do it that way? We can do it that way. Now you know what, we're going to cross multiply. There we go. We'll do it that way. T. It'll all work out either way. We'll cross multiply. I think most people would see that as an easier first step if you're not too familiar with this. So we're going to cross multiply. And now I'm going to go ahead and distribute the T here, and I'll distribute this. So this is going to be VT plus VOT, I distribute that, equals 2x minus 2x sub 0. Now, remember I want to get V by itself, so I'm going to take this whole thing here, and I'm going to subtract VOT from both sides. That's going to give me VT equals 2x minus 2x sub 0 minus VOT. Last thing I'm going to have to do here is I'm going to have to divide everything by t to get rid of this t here. So I'm going to divide each of these terms by t. that's going to give me final velocity is equal to 2x over t minus 2xo over t minus VO, because when I divide here, those t's are going to go away. All right. I'm trying to decide whether I want to let's simplify this a little bit. Let's take, we'll leave it. What the hell? So, V is equal to this mess. V is also equal to this. That allows me to set this equal to this. So I can write AT plus VO equals 2x over t minus 2xo over t minus V sub O. Now, I don't know about you, but most people don't enjoy these fractions, having a variable or something in the denominator here. But there's a way to get around that. What we can do is multiply everything by t. That by t, that by t. Multiply this by t, here by t, and that by t. And what that will do, in the case of here and here, is get rid of the t in the denominator. Now in the other ones, it does something slightly different. Here, for example, I end up with a t squared, t times t. Here, I just end up with VOT, the two times each other. Here, the t's gone, so I just have 2x, and then here I have minus 2x original, and then I have minus VOT. I think I'm going to, let's rework this for x. So that means I'm going to add 2xo to both sides. And while I'm at it, I'm also going to add VOT to both sides. Ooh, let me put this over here, because we can actually combine the VOTs. They are the same term. So I have AT squared plus, that's right here, plus these two combined, which is 2 VOT plus this thing, 2XO, is equal to 2x, the only thing left on that side. And I'm going to reorder this. I'm going to write this as 2x equals AT squared plus 2 VOT plus 2XO. The last thing I have to do to get x by itself is I'm going to divide everything by 2. And when I do that, it's going to cancel over here. I'm going to have x, which is what I wanted. Over here, I'm going to write this, so I have a times t squared divided by 2. Another way of saying that is half of a t squared. Same deal. Here the 2's cancel, and I end up with just VOT. And here the 2's cancel, and I end up with XO. And this is our second kinematic equation. Notice the variables are x and t. Notice also that it's a quadratic, which if you look, we've talked about graphing, we know that when there is acceleration, the position versus time graph will be in the form of a parabola. The initial conditions are the acceleration, the original velocity, and the original position. This is what I refer to as the second kinematic equation.